So the question here is, in a semiconductor, if the Fermi energy level lies in the conduction band, then the semiconductor is known as option A, degenerate N-type, option B, degenerate P-type, option C, non-degenerate N-type, option D, non-degenerate P-type. And this is the question they had asked in GATE 2023 for EC as a MCQ of the question. So in the question itself, what they ask about that if the Fermi energy level lies in the conduction band, then it indicates which type of the semiconductor. So this is the energy band diagram shown here for N type of the semiconductor, and as we know that if Fermi energy level is near about to the conduction band, this should be N type of the semiconductor. So this P type is not possible, and by that way option B and D is discarded here. Now for this N type of the semiconductor, whether it is degenerate or non-degenerate, we have to discuss here. So as we know that the Fermi energy level for this N type of the semiconductor is given by the expression of EF is equal to EC plus KT by Q into ln of ND by NC, where NC is the effective density of a state's function in the conduction band and ND is called the doping of the semiconductor. So for N type of the semiconductor, as per their approximation, the concentration of electron is approximated to this ND itself. And here if you see that this ratio, when it will be greater than 1, if ND is greater than NC, then this ratio will be greater than 1 and their ln values will be positive here, and due to that reason this term will be adding with the terms of this EC. So in that situation EF will lie in the conduction band, and we know that if ND is greater than NC, then it is called as degenerate semiconductor, degenerate N-type semiconductor. If this ND is lesser than NC, if the doping of the semiconductor is lesser than NC, then in that situation this ratio will be lesser than 1 and their ln will produce here as a negative values. So it means that level EF will lie below of this EC because this term will become here negative. So by that time it will be non-degenerate N type of the semiconductor. So we can write here if ND lesser than NC, then it is called as non-degenerate N-type semiconductor. So in the question itself it has given Fermi energy level lies in the conduction band. If it is lying inside the conduction band, it means it is justifying for this first condition here, ND will be greater than NC, and in that case we can say that the type of the semiconductor is degenerate and Fermi energy level is lying inside the conduction band or near to the conduction band, so it is called N type. So ultimately the answer will be degenerate N type semiconductor, and by that way the final answer for this question is option A, and by this way this is the end of the explanation for this question. So the question here is, for an intrinsic semiconductor at temperature T is equal to 0 degree Kelvin, which of the following statement is true? Option A, all energy states in the valence band are filled with electrons and all energy states in the conduction band are empty of electrons, full stop. Option B, all energy states in the conduction band are empty of electrons and all energy states in the conduction band are filled with electrons. Option C, all energy states in the valence and conduction band are filled with holes. Option D, all energy states in the valence and conduction band are filled with electrons. So this is the question they had asked in GATE 2023 for EC as a MCQ of the question. And this is very simple question from the semiconductor physics part. So this is the energy band diagram for the semiconductor. For the intrinsic semiconductor, it is shown here, and this is their crystal structure. So how the electron is moving from valence band to conduction band? If thermal energy is provided to this crystal structure, then by that time this covalent bond is breaking and some of the electron is migrating from valence band to conduction band. This is possible only if some thermal energy is provided. But here in the question it has given that at T is equal to 0 degree Kelvin, there is no thermal energy provided to this crystal, so that all these electrons is residing in the valence band in the form of covalent bond. So we can say that all the energy level in this valence band is completely filled by their electron. So we can say that this valence band is completely filled by electrons. And if there is no breaking of the covalent bond, it means there is no electron migrating from valence band to conduction band. So by that way, we can say that this conduction band is completely empty of electrons. This is completely empty of electrons. So in that way, we can say that in option A, it has given all energy states in the valence band are filled with electrons. Yes, so this valence band is completely filled. There all the energy state is occupied by the electron in the form of covalent bond. And all energy states in the conduction band are empty of electrons. So in this conduction band also we have many more energy states. But due to the absence of electron, no energy state is occupied by the electron, so we can say that it is completely empty of electron, and by that way option A is the right answer for this question. And by this way, this is the end of the explanation for this question. So the question here is, for a MOS capacitor, VFB and VT are the flat band voltage and the threshold voltage respectively, full stop. The variation of the depletion width as a W depletion for varying gate voltage as a VG is best represented by, and their graph is given in all these four options A, B, C, D. So this is the question they had asked in GATE 2023 for EC branch and from the topic of MOS capacitor. So this is also one of the MCQ of the question. So now here if you'll see that they are asking about that how this depletion region is varying with respect to the gate voltage. So first of all, we know that this MOS capacitor works into three regime of operation. One is called accumulation regime, second one is called depletion regime, and third one is called as a inversion regime. And as we know that in the accumulation regime, there is no such kind of depletion region formed in the semiconductor or over the surface of the semiconductor. So that is the reason there is no depletion region in the accumulation regime. And as per that point, we can say that option C is discarded here, because in the accumulation regime also it is showing some part of the depletion region, but this is not here in the case of MOS capacitor in accumulation regime. Now depletion region is formed in which regime? Depletion regime as well as in the inversion regime, and how it is relating with the gate voltage. So depletion region formula it has given W depletion is equal to square root of 2 epsilon by Q into 1 by semiconductor doping as a Ns into magnitude of surface potential. So this surface potential is directly related to this gate voltage as a Vg. So it means we can say that this W depletion is also relating to directly proportional to a square root of Vg. Now, if you see that this depletion region is varying with the gate voltage, so here with the relation of non-linear as a square root, and that is the reason in option A and B, if you compare that this part and this part, so here it is saying that if gate voltage is increasing, then their depletion region magnitude will be lesser because of this square root. So that is the reason compared to A. B is the rightmost option here. And after that, we know that in the inversion regime, so in the depletion regime, as per as this Vg is increasing, this gate voltage is increasing, this W depletion is also increasing. But at threshold voltage, at this point of time, at threshold voltage, whatever is the depletion region formed, that is called their maximum depletion region, and by that time it is going to be saturated. So here in the option D, if you see that in the inversion regime, it is not showing any depletion region, but it is there with the constant value. So that is the reason option D is also discarded here. And now from A and B, this which option will be right? So this is giving the indication that in this part also it is constant, in this part also it is constant. Means in the inversion regime, this depletion region must be saturated and that should not change. But in depletion regime, it should relate with this relationship, with the square root of Vg. So if Vg is more, then W depletion will be lesser compared to this option A. So their magnitude should be lesser because of this square root. So the best describing option for this graph is option B. So option B is the right answer for this question. And by this way, this is the end of the explanation for this question. So the question here is, in an extrinsic semiconductor, the hole concentration is given to be 1.5 Ni, where Ni is the intrinsic carrier concentration of 1 into 10 raised to 10 per centimeter cube, full stop. The ratio of electron to hole mobility for equal hole and electron drift current is given as, fill in the blanks, as a round off to 2 decimal places, full stop. So this is the question they ask in GATE 2023 for EC as a numerical answer type of the question from this ADC subject. So this is also one of the very simple question, and here it has given as per their given data. So given hole concentration as a P is equal to 1.5 Ni, and their Ni value has given as a 1 into 10 raised to 10 per centimeter cube. And we know that as per the mass section law, if the hole concentration is given, we can easily find out their electron concentration. So here, as per mass section law, we can easily find out the concentration of electron, as this will be N is equal to Ni square divided by the concentration of hole as a P. So this can be written here as a Ni square divided by 1.5 Ni. So 1 Ni from here it will be cancelled out. So this is giving here as a Ni divided by 1.5. And next part of the question they had given that the ratio of electron to hole mobility we need to find out for equal hole and electron drift current. So they are asking that hole and electron drift current are equal. In that situation, what will be the ratio of electron to hole mobility, that we need to find out. So as we know that this Jp drift, how it is, this Jp drift, it is given here, Jp drift is equal to Jn drift. So here we know that this Jp drift is given as a PQ mu P into E is equal to NQ mu N into E. So this E is the electric field, mu P the mobility of the holes, mu N is the mobility of the electron, Q is the electronic charge, and P is the concentration of hole and N is the concentration of electron. So by equating these two, this is cancelling here this electric field and electric field. This is cancelling the common term as a Q and Q. And now we need to find out the ratio of electron to hole mobility. It means we need to find out mu N by mu P. So mu N by mu P means it is given by P by Ni. So P concentration is how much? P concentration is 1.5 Ni, and there, this is not Ni, this is N here. So P by N, so P concentration is 1.5 Ni, and this N concentration is given here as a Ni divided by 1.5. So from here, this Ni gets cancelled, and we got it here 1.5 into 1.5, which is equal to 2.25. So the ratio of mu N by mu P, we got it here as a 2.25, and this is the final answer for this question. So the numerical values will be 2.25 here, this is 2.25 here, and by this way, this is the end of the explanation for this question. So the question here is, in a semiconductor device, the Fermi energy level is 0.35 electron volt above the valence band energy full stop. The effective density of states in the valence band at T is equal to 300 degree Kelvin is 1 into 10 raised to 19 per centimeter cube full stop. The thermal equilibrium hole concentration in silicon at 400 degree Kelvin is, fill in the blanks, into 10 raised to 13 per centimeter cube, and answer should be round off to 2 decimal places full stop. Given value is given, KT at 300 degree Kelvin is 0.026 electron volt. And this is the question they had asked in GATE 2023 for EC as a numerical answer type from the subject of EDC and on the topic of semiconductor physics. So in this question, what they had asked to find out? They had asked to find out the concentration of holes. Here it has given thermal equilibrium hole concentration in silicon at 400 degree Kelvin. And this is the energy band diagram for P type of the semiconductor. So here Fermi energy level, like it has given 0.35 electron volt above this valence band. So this is shown here. This EF is lying above this EV by the amount of 0.35 electron volt. So by the use of this data, we need to find out the new concentration of holes at 400 degree Kelvin. And we know that in terms of energy level, how to find out their concentration of the hole. So it is given P is equal to NV exponential of minus under bracket EF minus EV by KT. And this NV is called states of the function in the valence band, and it is given here this NV is equal to 2 into under bracket 2 pi MP star KT by H square and whole power 3 by 2. So this MP star is called effective mass of holes, K is Boltzmann constant, T is temperature in degree Kelvin, H is Planck's constant. So here it is giving the indication that this NV is the function of temperature here, remaining parameter are constant, and this P is the function of NV. So it means P is the function of NV and NV is the function of temperature. It means P is the function of temperature indirectly. And here also at the numerator part of this, it is given as a KT. So KT is also the function of temperature. It means whatever it is given the data, as per that we need to find out the whole concentration at 400 degree Kelvin. So here the given data is, here it is given EF minus EV is equal to 0.35 electron volt, and here it has given at 300 degree Kelvin at T is equal to 300 degree Kelvin. The KT value it has given as a 0.026 electron volt. And we know that thermal equivalent voltage, how it is relating with this KT. So this thermal equivalent voltage VT is given as KT by Q. So here, if you take this as a KT by Q or KT by E, then this value will become here as a 0.026 volt. So it means this E or Q we can use interchangeably. So this KT by Q can be written here as a thermal equivalent voltage VT as a 0.026 volt. So now this KT value or this VT value will change if the temperature will change from 300 to 400 degree Kelvin. So we can find out here, this is giving the indication this thermal equivalent VT is directly proportional to temperature, because this K and Q, this K is called Planck's constant and Q is called electronic charge. So this K by Q is a constant value and this is not depending upon the temperature. So this VT is depending upon this temperature here. So VT is directly proportional to T. So we can write down here as a VT1 divided by VT2 is equal to T1 by T2. So we need to find out here VT2. So this VT2 will be T2 by T1 into VT1. So this T2 it has given 400 degree Kelvin. So 400 degree Kelvin and T1 is 300 degree Kelvin into VT1. We got it here as a 0.026 volt. So after calculating this, we will get it here as a 0.03466 volt. So this is the value for VT2, and VT2 is what? This VT2 is equal to KT2 divided by E. So this is giving here as a 0.03466 volt, or we can write it here as a KT2 value, because we need to find out this whole concentration at T2 temperature. So we need to find out the value of KT2 at T2 temperature as a 400 degree Kelvin. So this KT2 at 400 degree Kelvin is 0.03466 electron volt. This value we need to use for the further calculation of this P value here. So we got it here, KT2 value, and now at this temperature we need to calculate this NV value. So now we'll calculate this NV value. So as we know that this NV is having the expression as like 2 into 2 pi mp star KT divided by h square raised to 3 by 2. So in this case also that apart from temperature, rest of the terms are constant at a given temperature. So here this NV is directly proportional to T raised to 3 by 2. So with respect to given NV value, we can easily find out the NV value at the new temperature. So here we can find out this as a NV1 divided by NV2 is equal to T1 divided by T2 raised to 3 by 2. So from here we can get it NV2 is equal to T2 by T1 raised to 3 by 2 into NV1, and now we need to substitute the value of T2, T1. So T2 is 400, T1 is 300 raised to 3 by 2, and their NV1 value, it means the given NV value in the question itself is 1 into 10 raised to 19 per centimeter cube. So after calculating this, we will get it here as a 1.5396 into 10 raised to 19 per centimeter cube. So now we need to use this KT2 and NV2 to calculate the whole concentration at T is equal to 400 degree Kelvin. So we'll use this equation here. So this P is equal to NV exponential under bracket minus EF minus EV divided by KT, or here we can say that KT2, because we are calculating this concentration of hole at T2 temperature, which is basically 400 degree Kelvin. So at 400 degree Kelvin we got it here as a NV2 value. So we need to substitute in this equation. So we'll get it here. This is 1.5396 into 10 raised to 19 into exponential of this EF minus EV value it has given in the question as a 0.35 electron volt, and KT2 we had calculated as a 0.03466 electron volt. So this electron volt and this electron volt is cancelled to each other, and this is having only the ratio with this negative sign. So whenever you will calculate this, it is coming here as a 6.336 into 10 raised to 14 per centimeter cube, but in the question itself it has given the order as a 10 raised to 13, so we can convert this into 10 to the power 13. So this can be written here as a 63.36 into 10 raised to 13 per centimeter cube. So we got here this whole concentration as a P is equal to 63.36 into 10 raised to 13 per centimeter cube. So as this question is numerical answer type having this value mentioned in that, so the numerical value for this question it is 63.36. So here in this question itself it has given here this 10 raised to 13 already it has mentioned here, so their numerical value it will be 63.36. So the final answer for this question is 63.36 as their numerical value, and by this way this is the end of the explanation for this question.